Okay, this is 8.3 combinations. So we did permutations before. Combinations are similar, but here's the key thing. A combination is a collection of items where order does not matter. That's the key thing. When we did permutations, order mattered. So the formula should look really similar, right? N choose R. We had N over R, and then N minus R, N factorial and N minus R factorial. The only thing we've added here is this extra piece here, okay? So let's just do it by example. That's the easiest way. So what you got is you got 170 students registered for pre-calculus MAP40S. In how many ways can 25 of these students be selected for one slot class? So it doesn't matter what order you pick them in, right? Who cares which order you pick it in? So it's 170, choose 25. So we use a combination since order does not matter, okay? And then all we do is we plug in the numbers right into the formula, 170 factorial over 25 factorial and 170 minus 25 factorial. We get this big old number here. Now you stop there, right? Because you actually can't do that calculation because the number would be so large. We can just leave it in that form. Okay, next one. Calculate 5 pick 2 and 5 choose 2. So the first one's a permutation, the second one's a combination, but we're using the same numbers. So 5 pick 2 is 5 factorial over 5 minus 2 factorial. The 5 choose 2 is 5 factorial over 2 factorial, 5 minus 2 factorial. And you go through, you can see we've done the math here, and 20, and this one has 10. So when order doesn't matter, who cares? You have actually less combinations. So combinations will always be smaller than they will be for permutations, okay? Notice that when you give a number of items, there's always a less number of combinations, less number of permutations. Okay. Example 3. Calculate 8 choose 3 and 8 choose 5. And there's a reason for this. So we do all the work here, right? 8 choose 3. Now you can see the whole pattern here, right? There's the formula. 8 choose 5. There it is there. And if you look, we actually end up with the exact same answer. So it's kind of neat. So it's no coincidence these two expressions are equal. So here's the basic breakdown. N choose R is the same as N choose N minus R. So what I can do is I could give you a question like where I ask you to go backwards and find out what N choose R was, right? And you'll see right away. So this could be anything, right? 10 choose 6 is the same as 10 choose 4, right? 3 choose 1 is the same as 3 choose 2, right? Every time it works out in this case for combinations. Okay, page. Let's go to, oops, sorry. Example 4. Bridge, it's a game people play with cards. So it consists of 13 cards, and how many ways can a hand containing 3 aces be dealt? Okay, so think about this. 4 choose 3. Why is it 4 choose 3? Because the order doesn't matter than picking the aces, but there's 4 aces in a deck, and we choose 3 of them. Okay, then we've picked 3. We have to fill all the rest of the cards, the 10 of them, right? Because there goes our hand of 13, right? 3 and 10 is our 13. And there's 48, right? There's 52 cards in the deck. We've already picked 4 of them, so then it's 48, choose 10. And we multiply this because it's not the aces or this, it's the aces and the other 10 cards. So we have the and, so then we have the multiplication. Okay, so this is a really neat example, I think. So example 5, from a group of 10 people, we're making a committee. And a committee of 3. And there's some restrictions on this, right? 3 be chosen if Roger and Ellen refuse to be on the committee together. They don't like each other, right? They've been, oh, they fight every time they're on. So let's look at the left-hand side here. So what we can do is we can do case 1. Case 1 is just Roger. So the first position, yeah, would be Roger. There it is there. And then we have to fill the other 2 spots from 8, right? Because we can't use Ellen. So it's 8 choose 2, right? And we do the math there and we get our 28. What if it was just Ellen? Same thing with Roger, right? The one position is Ellen, and then we 8 choose 2. Because there's 8 people left, choose 2. What if it was neither Roger nor Ellen? Well, it's 8 then, because we don't include those 2 in our big calculations of 10. There's only 8 of them, and we're choosing 3, and we get 56. So this comes the case we did on tail end of 8.2. It's this, or this, or this. Right, so you add them together 112 ways. Now that's the normal way of doing it, right? You do just Roger, just Ellen, or neither. Here's a cool way of doing it. Think in a different perspective. Think if there was no restrictions at all. So if there was no restrictions at all, it would be 10 choose 3, right? 10 people were choosing 3, we get 120. What if both Roger and Ellen were on the committee? And we know that can't happen, but what if they were both on the committee? So it'd be 1 for Roger and 1 in Ellen. So it'd be 8. Choose 1 in this, 1 for Roger, 1 for Ellen. The other spots, there'd be 8 left over, and we choose 1, we get 8. Okay, now, but look, here what we got. We got 120 for no restrictions. Both Ellen and Roger, which we don't want, is 8. So in that case, we don't add, we can subtract. And if you notice, we end up with the exact same answer. So this type of question, you can either approach it 2 ways. You could do your individual case studies and add them all together, or think if there's no restrictions and then subtract it out of that. It's just another way to think about it. Okay, third page. So third page is what it is expressed as factorials and simplify. So what we have here is n choose 5 and n minus 1 choose 3. So what we do is we break the first one. Here's the formula right here for the first part. N factorial over 5 factorial, n minus 5 factorial. We break the bottom part down, so n minus 1 factorial over 3 factorial, n minus 1 minus 3 factorial. So all we've done is taken this whole thing and broke it down into its formulas, okay? Now, we know when we're dividing by something, it's the same as multiplying by the reciprocal. So the first one stays the same, and we multiply by the reciprocal. Perfect. Now what we can do is we can start eliminating stuff. So this first one, we can go n, and remember, factorials mean we go down, so we can do an n minus 1. Oh, cool. We can do an n minus 1. You can see they're going to cancel top and bottom. This one, we can take the n minus 4 and go n minus 5. It's going down one more. Oh, yeah, n minus 5 and n minus 5. So that one disappears, that one disappears, that one disappears, that one disappears. Now, you also have 3 factorial. So 5 factorial on the bottom here is 5 times 4 times 3 factorial. Bang, you can knock those off too. So what you can do is you can eliminate a ton of stuff just by doing the factorials. So then what are we left with on the top? N times n minus 4, and we're left with 5 times 4, which is 20 on the bottom. Perfect. You don't have to go any further. You can leave it as that. So we expressed this initial one as factorials, and then we simplified it down into this last piece. Okay. Last example here. On 8.3, solve now. This is a little different. Last one was simplify. This one we're going to solve, but we're going to do the same thing. So if you look, this is 2 times n choose 2. So what we can do is take this n choose 2 right here, and we can break it down into its combination formula. There it is there. We take the n plus 1 choose 3 and break it down into its formula here. Okay. Careful on this one here. This is this n plus 1 minus 3 at the bottom, which is your n minus 2. Kind of nice. Now what we do is we can try to eliminate as much as we can. And you can eliminate either up and down or diagonally, right? So this n we can break down, well, this n we can break down into n minus 1, n minus 2. Useful because we could take it n minus 2 out of here and n minus 2 out of here, or you could go a different direction. This one, this n plus 1 would be then n minus 1, n minus 2. Again, we can knock those 2 out because they're the n minus 2s. Now, here we have an n factorial, so that's n times 1, so those 2 are gone. Now here's an interesting concept. You got to kind of look at this. If you notice, I've crossed off n and n minus 1, but they're not up and down or diagonally. But look here, you can get rid of n by dividing both sides by n. So for instance, if I divide the right side by n and the left side by n, doesn't change the overall thing. They disappear, right? Because you can divide them out. You can also divide by n minus 1, n minus 1 both sides. So if I divide this side by n minus 1 and the left side by n minus 1, bang, they disappear also. So it's another way to look at this when you're trying to reduce factorials, okay? Because we reduce all of this on one side, look at this, everything's gone. Now don't forget, if it reduces down, it doesn't cancel, which is 0, it reduces, which is 1. So we have 1 on the left-hand side. And then what we're left with over here on the right is n plus 1 and 3 factorial, and 3 factorial is just 6. We cross multiply, so 1 times 6, right? So 6 equals n plus 1, and then 5 equals n, right? So that big complex combination, we were able to break down into just 5. So the hard part for you will be in here, will be canceling on the left side and right side, right? You just have to kind of remember this rule here as you go through them. So keep this, as you're doing the questions, right? Keep this in front of you to help you with that. Okay, so that is a brief overview of 8.3. So the only thing left is 8.4, and that'll be the next lesson coming up.